Okay, today's video we're going to continue with our discussion of the Riemann sums with our summation notation, and we're going to add on a discussion of what a definite interval is. So we're going to go back to our discussion with the Riemann sums, and we've been approximating area under the curve, and I'm going to remind you that when we've been doing this that we're really talking about net area or the accumulation function, where when we accumulate area, if the function is a positive or above the x-axis, then you would add area, but when the function is below the x-axis, you would take area away. So this is the idea of net area or net accumulation, and we've been using rectangles and trapezoids to do them with Riemann sums. So we're going to come back in and take a look at another example. So we're going to graph cosine of x on the interval from 0 to 2. Now, just reminding you, cosine, the quadrantal angles, 1.57 is about pi over 2. That pi over 4 is about 0.7-ish, so that would be about right there, halfway in between. Pi over 3 is a little bit more than 1, so kind of adding these in. And pi over 6 is about the same distance, somewhere over here, a little bit more than a half. And so kind of putting in a cosine curve, we know that it starts at a max. We know that the cosine of pi over 3 is a half, so I'll add that in. Pi over 2 is 0. And 2 pi over 3, 6 divided by 3 is a little bit more than 2, so that's where that 2 pi over 3 family member is, and that's negative 1/2. Now we're going to stop it right at 2, so it'll be a little bit above that when I sketch it. So it's going to come down, hit my pi over 2, and it's going to be a little bit above 2 here, and so kind of curve it so that it's concave up there. So that's the function that we're kind of taking a look at. I'm just going to make this a little thicker as I go down through here. So we want to know kind of this idea of examining this, and we're going to use a right Riemann sum, so that's important to note. It's also important to note that we want to use 4 subintervals. So n is going to be equal to 4. And we want to approximate the area under the curve. And again, I'm going to stress that this is net area under the curve. So the first thing, we're going to calculate how wide is each rectangle. So delta x, remember, is b minus a over n. So that's going to give us our a and our b are up here in this interval. So 2 minus 0 over 4, or the width of each rectangle is going to be 1/2. So taking a look at these rectangles at 1/2, remember our height comes from the function value. So this would be our first right rectangle. And then at 1 would be our second right rectangle. At 1.5 would be the next rectangle coming across, really short little rectangle here. And then at 2, remember it's a right rectangle, so it would come across and be there. So taking a look at our actual area that we're going to use to approximate, I'm going to highlight it here in blue. And so that's going to be our 4 rectangles we're going to use to approximate our area under the curve. So I'm just going to move over because I know I need room. So net area from 0 to 2 can be approximated with a 4 rectangle right Riemann sum. Our width is 1/2. The height of the first rectangle would be cosine of 0.5. Remember, because we're getting the function value here. Remember, this is 0.5, and then the y value, or the height, is going to be the cosine of 0.5, and so on, continuing through. So the next rectangle will be 1/2 cosine of 1, then 1/2 cosine of 1.5, and 1/2 cosine of 2. Now, when we look at this, just as kind of why this is net area, remember that that value is negative, but these are positive heights as you go down through here. So this is also the reason why this is net area, not total area. total area would always be positive, where you would add the area above plus the area below. But net area means we gain area up until pi over 2, and then we lose area from pi over 2 to 2. All right, and then if we add that together, just arithmetic using your calculator, this would be approximately 0.536. So that gives us an approximation of the net area using 4 rectangles. So we come in and we say, do we think this is a good approximation? And I do hope that you would look at this and you would be like, hey, this is not a great approximation. If we look up here at our curve, and I'll just put this in yellow right now, that when you look at this, there's all of this kind of unused area under the curve here, which means that we don't have enough area in our approximation. And also, this part right here is too much being taken away. And I will remind you that we learned in one of the previous videos that a right Riemann sum is an under approximation. So the right Riemann under approximates, and this is actually under approximating by quite a lot. There is a large amount of area not accounted for. And we also see that, and it might bother you down here at the bottom with the negative area, that it's actually the rectangle is extending beyond it. But remember, this is still an underestimate, because that means that I took away more area than I should have. And so it's still going to make it be an underestimate. So no matter whether the function is above or below, the right Riemann sum always under approximates the area. So this is not a great approximation. So then the next question comes in, and we ask ourselves, well, what if I were to use 8 rectangles? So let's go through and look at that. Our delta x is going to change. So our delta x is now going to be 2 minus 0 over 8, or a fourth. I'm going to go ahead and do it as a decimal, 0.25, a little easier to do. I don't want to deal with the fractions right now. So if I want to approximate this net area from 0 to 2, then what we want to do, we're going to do this with a right Riemann sum with 8 rectangles. And we're just going to go through and we're going to write them out. Remember that your width is now 1/4. Your first one, if I come up here and I start sketching it on here, now we're going to be going to a fourth. So our first rectangle would be this portion right here. Our second rectangle would be over here to the 1/2, and then so on. Adding these rectangles in, you start to see that our approximation, of course, is going to be a much better approximation than it was. So this is what your 8 rectangle one is going to look like on that. Okay? So our first one would be at 0.25 plus 1/4. Our next one would be at 0.5, and so on. And as you're kind of getting into the flow of filling these in, especially if you're on the AP, make sure that you're counting how many rectangles you have, because you kind of get in the flow of writing this down. You forget when to stop. I'm going to come down here below for the next 4, because that way I want to make sure I have 8 rectangles. So we would have cosine, what are we at, 1.25, cosine of 1.5, cosine of 1.75, and then cosine of 2. And it's very easy to, when you're doing the right Riemann sum, it actually is nicer because you end at the b value in your interval, the end of your interval. But if you were doing a left Riemann sum, remember you would stop at 1.75 because you would have been including cosine of 0 over on the beginning. But make sure you count that you have 8 of these sums being added to 1 for each rectangle. All right, and this ends up being approximately 0.728. Now, hopefully, you would agree that this is a much better approximation. You can see that our little leftover areas have been reduced a little bit, the yellow areas, because I've included them kind of here. I've added this into it. I've added some extra here, so that and I took out some area down here at the bottom that I was subtracting. So is this a good approximation? Oh, no, that's still a rough estimate. I would say it's better than 4, but still not great. I think we can do better. So kind of as we go through this, given these two approximations, I would say, could you guess what you think the true area is? So go ahead, you guys write down what you think your guess is. Okay. Remember, we got our 0.536 for 4 rectangles, our 0.728 for these rectangles. Go ahead, write it down, put it in a box. Now, I will tell you, of course, everybody's answer is going to vary, but I will tell you that I hope that your guess should have been greater than 0.728. And the reason for the fact that your guess needs to be greater than 0.728 is to remind yourself that the right Riemann sum underestimates when your function decreases, f of x decreases. So hopefully everybody's guess was a little bit more than that. So then the question becomes, what would be, how many rectangles do you think you need to have in order to make a pretty confident guess? And so, I don't know, hopefully you'd say, I really want a lot. Okay, and so this is one where the idea is, hey, good thing we know calculus, because we will remember that what we've done before is that what we're going to add to this is a limiting process, okay? And if we add a limiting process, this is what turns this nice calculus rough estimate into the exact value. So this limiting process that we're going to add, can you think about what we want to do? We would like to make sure that we have more rectangles. So we're going to take the limit as the number of rectangles goes to infinity of this sum that we're doing, right? And we're summing I equals 1 to n of the rectangles of the height of the rectangle, which came from the function value, times the width of the rectangle, which was delta x. All right, we're going to go to the next page now, and we're going to summarize some new things that we want to learn. We're going to learn some calculus. All right, so we can see here several right Riemann approximations, and remember, they're all underestimates, where we increase our number of rectangles from 12 to 20 to 50 and then to 100. And even with 100, even though I can't really see it, there is still some gaps in there if we zoom in far enough. But kind of as we increase the number of rectangles, what happens to the width? So as n goes to infinity, delta x is going to approach 0. It's going to get smaller as we go. And then could we do another best guess for this? Now, right now, we're up to about 0.89511. But remember, it's still an underestimate. So your guess right now should be greater than 0.895. But I will tell you that you see we're getting closer and closer to the approximation. So I would say that you're not too much bigger than that. I'd probably guess around 0.9. If I was doing this, maybe 0.905, I don't know, something larger than 0.895, but not too much larger, because we know that we're still underestimating. So the idea here is how many rectangles would be needed to get the exact area under the curve? It would be infinitely many. And so that's why we're going to apply the limit as n goes to infinity. All right, so let's show the calculus that we're going to do. All right, so to finish this video out, what I want to do is to talk about how our summation notation is what we call a definite interval. So I'm looking over here at this integral notation, kind of, this is my target for this last few seconds of this video, that the limit of a sum of areas turns into what's called a definite interval. And a definite interval, or notice that we have our uppercase sigma, that's the limit of a sum. Our height is now f of x. Notice I don't say x sub I, because it doesn't really matter if you do left, right, middle point at all. Your delta x becomes dx, which is your variable of integration. All right, so that's going to finish this video up. Try to check your understanding, and we'll come back and summarize.